There's a moment at every airport check-in counter that nobody talks about. You hand over your bag, the agent tags it, and then it slides through a rubber-flapped opening in the wall. And it's gone. You don't know where it goes. You don't know who touches it. You won't see it again until a carousel spits it out at your destination, assuming it arrives at all. That anxiety you feel watching it disappear, it's not irrational. It's a rational response to a system that was deliberately built to be invisible. Most passengers assume the bag enters some kind of storage room where workers sort it by hand. It doesn't. The moment it clears those rubber flaps, it enters a network, a miles-long mechanical infrastructure running beneath the terminal floor, moving 20,000 bags simultaneously through lightless tunnels without a single worker directing any of them. What actually happens in those tunnels is more calculated than most passengers ever suspect. The first thing to understand is that this isn't a conveyor belt. What sits beneath a Tier 1 international hub is something engineers call a tilt tray sorter, a continuous loop of individual flat trays, each carrying one bag, traveling at roughly 20 miles per hour. Think of it less like a factory production line and more like a highway interchange, where every exit decision is made automatically, in under 50 milliseconds, for every single vehicle, without stopping traffic. Now, where it gets interesting isn't just that the loop moves at 20 miles per hour, it's that the machine has to make a life or death decision for your luggage every 50 milliseconds. But to do that, it needs to see in the dark. The loop never pauses. It doesn't wait. It runs continuously, 24 hours a day, reading and routing every bag that enters it. But before a tray can route anything, the system needs to know where the bag is going. That's handled by the automatic tag reader array, a scanning tunnel the bag passes through at full speed. Inside that tunnel, roughly 30 laser beams fire from every angle simultaneously, reading the barcode on the bag tag from above, below, and both sides at once. The bag doesn't slow down. It doesn't stop. It moves through at pace, and by the time it exits the tunnel, the system has already matched the tag to a destination and assigned the tray a divert command. A useful way to think about it: imagine a toll booth that reads your license plate perfectly from every direction while you're doing 60 miles per hour. That's the operational reality of an automatic tag reader array. Now, here's where the math gets uncomfortable. Automatic tag reader accuracy at major hubs sits between 95% and 98%. That sounds reliable. In isolation, it is. But at 20,000 bags per hour, a 2% failure rate produces roughly 400 bags per hour that the system cannot identify. 400 bags every hour that the machine has no destination for. So what happens to them? Some carry what technicians call a zombie tag, an old sticker from a previous flight that the laser array picks up instead of the current one. The system reads a tag, finds a destination, and it's the wrong destination entirely. Others have tags that are torn, angled, or printed faintly enough that no laser can resolve them at speed. In both cases, the bag gets diverted off the main loop and into what engineers call the manual encode loop, a secondary circuit where unreadable bags cycle continuously until a human operator at a workstation reads the tag by hand and keys in the correct destination. It's the system's mechanical holding pattern. A bag can circle that loop for minutes. In a congested hub, longer. But there's a problem. No matter how many lasers you have, a physical system is only as good as its weakest mechanical link. And when this $500 million machine fails, it doesn't just lose your bag, it destroys it. Once a destination is confirmed, the routing decision passes back to the hardware. And the answer isn't a worker, it's a solenoid trigger with millisecond precision. A solenoid is a small electromagnetic coil. When it receives the signal, it fires a single electrical pulse lasting between 30 and 50 milliseconds, less than the time it takes to blink. And that pulse physically tips the tray, sending a 50-pound bag down the correct chute toward the correct aircraft gate. The machine reads, it decides, it acts. The entire sequence happens faster than a human can consciously register it. But what happens when the machine itself is the problem? One airport found out, and it cost them $560 million. In 1995, Denver International Airport opened 16 months late. The reason wasn't construction, it wasn't permits, It was a baggage system that had consumed $193 million in capital, required hundreds of additional millions to partially fix, and still didn't work. The original ambition was genuinely unprecedented. Denver's automated system was designed to connect 3 concourses, serve 20 airlines, and move bags through 21 miles of underground track using 4,000 autonomous carts. Each one independently navigating the network, picking up bags and delivering them to the correct aircraft without human intervention. No hub had attempted anything at that scale. The closest comparable installation was roughly 1/10 the size. The carts destroyed luggage. They collided with each other on the track, derailed at junctions, and when a bag had a protruding strap or an irregular shape, the system treated it as a mechanical obstruction and kept pushing. The hardware had been engineered around a single assumption: that every bag entering the network would behave like a uniform rectangle. A soft-sided bag with a loose handle was, to the system's logic, an error state it had no protocol for handling. In reality, Denver's failure wasn't just a glitch. It was a $600 million graveyard for suitcases. It forced the entire aviation industry to rewrite the laws of engineering. And the solution they found is the reason you can track your bag on your phone today. What made the failure particularly instructive was where it originated. The carts worked under controlled test conditions. Individual segments of the track performed within specification. The system had never been run at full operational volume before opening day, because there was no window in the construction schedule to do it. Engineers found out what the machine could not handle at the worst possible moment, with airlines waiting, passengers booked, and no fallback ready. The final accounting was $560 million in overruns. The airport delayed opening by 16 months. The automated system operated in partial capacity for one airline on one concourse for a decade, then was decommissioned entirely in 2005. What the industry built in response was a different class of machine entirely. The Destination Coded Vehicle, the DCV, replaced the concept of an autonomous cart navigating by dead reckoning with a guided system built around sensor arrays, redundant communication channels, and the ability to detect and respond to obstructions before contact. Systems using this architecture now operate at Heathrow Terminal 5 and Dubai International. The difference isn't simply speed or capacity. It's that the DCV was designed around the assumption that the real world contains irregular bags, worn tracks, and peak load conditions that no test environment fully replicates. The regulatory response came through the International Air Transport Association. Resolution 753, adopted as a binding industry standard, mandated that every checked bag be scanned and logged at 4 fixed points in its journey: check-in, aircraft loading, transfer, and arrival. Not as a courtesy update to passengers, but as a data record that follows the bag through the network. A bag that was previously a physical object with a paper tag became a tracked node, its location logged against a timestamp at every handoff point. That mandate, and the infrastructure required to fulfill it, is why a full Tier 1 baggage handling system installation today costs between $500 million and $1.1 billion. Denver didn't just expose what happens when the algorithm fails. It established the floor for what a system that doesn't fail actually costs. Your bag was never being handled. It was being calculated, routed through a decision network that reads, assigns, and physically acts on data faster than human cognition registers the question. The machine's indifference isn't a flaw, it's the design. If this kind of forensic investigation into the systems running the modern world is what you're here for, the next video in this series goes deeper. It's linked on screen now.